problem 3.4, calculate the following limits. Okay, so again, 8 different limits. Start with the first one. First is the limit when n goes to infinity of n over pi times the sine of n pi. So this is a classical example in which if you're not careful you will make a mistake. So here what you need to realize is that the sine of n pi is always 0. Okay, so when n is equal to 1, sine of pi is 0, the sine of 2 pi is 0, the sine of 3 pi is 0, and on and on and on. So every term in this sequence is identically 0. It's always 0. And so it doesn't matter that you multiply it by n, this is always going to be 0. So the limit of this sequence is 0. Okay, the whole sequence is always 0, so it's the limit is 0. Okay? Now, second is the limit when n goes to infinity of n times e to the 1 over n minus e to the sine of 1 over n over 1 minus n times the sine of 1 over n. Okay, so this let's see, so the denominator, this is something that's going to go to 1 because 1 over n is going to 0, so 1, and then the sine of 1 over n is also going to 0, so this is 1 minus 1, and this is going to infinity, so this infinity times 0 and then divided by 1 minus infinity times 0 again. So this is an indetermination in so many levels. Well, the first thing that I'm going to do is try to use some of the expressions that we derived in theory, try to see if we can write something like e to the epsilon sub n minus 1, okay? Because we know that when epsilon sub n is going to, if epsilon sub n is tending to 0, then this thing is very similar to epsilon sub n, okay? And we will understand why this is so again when we see Taylor expansions later on in the course. But I'm going to try to rearrange things so that I have some expression like this in the numerator, okay? So the first thing, I'm gonna divide by n both the numerator and the denominator. So then we have e to the 1 over n minus e to the sine of 1 over n, and then this is 1 over n minus sine of 1 over n. Okay, so as you can see, we have in the denominator we have the subtraction of the exponents in the numerator. Okay, but this expression is going to 0, right? Because this is going to 0 and this is going to 0. So maybe I can use this sequence as 1 over n. Okay, so sorry, as epsilon sub n. So I just need to do some algebra in the numerator. So if I multiply and divide by e to the sine of 1 over n, then the numerator is like this, e to the 1 over n minus sine of 1 over n minus 1. Okay, so I'm just multiplying and dividing, or if you want, taking the common factor, and then in the denominator we have this. So again, this sequence is going to 0, so this thing is going to be very similar to this thing when n is large. Okay, so in other words, this term is going to tend into 1. Okay, so now my limit is just the limit when n goes to infinity of the sine, the e to the sine of 1 over n. And this is just the limit of this, okay? It's e to the limit of the sine of 1 over n. And again, this is the sine of the limit, but we know that when this n goes to infinity, this goes to 0, the sine of 0 is 0, so this is the limit is e to the 0 or 1. Okay? goes to infinity of n divided by the square root of, the nth root of n factorial. Okay, so whenever you have a factorial in the limits or series or whatever you want to compute or calculate, I suggest you use Stirling's approximation, which says that this is approximately equal to this, well, asymptotically equal to this when n is very large. Okay, so and we know that we can substitute this in limits when they're in fractions. Okay, so this is the same in n over, and then the nth root of n to the n, which is n, the nth root of e to the minus n, which is e to the minus 1, so I can just write it here, and then the nth root of this, so this is, let's see, let me write it like this. This is 2 pi n to the 1 over 2, but then it's 1 multiplied by n, so it's 1 to n. Okay. So then now we have n and n cancel each other out, and this thing we know it's going to 0, because in other words we can write it like this. This is the nth root of this, and then this is the square root of, well, no, yeah, sorry, I'm just reading. We can write this like this. This is the nth root of the square root of 2 pi times, and then it's the square root of the nth root of n. Okay, we can write it like this. So okay, so this is any, it's a positive number a, and we know that the limit of this, the limit when n goes to infinity of the nth root of a is 1, and then the limit of this, we know that it's 1, and so the square root of 1 is just 1. Okay, so this is just e. Okay. But there's another way to do this, and this is to see that both, let's see, well, yeah, we can rewrite it like this. Sorry, this is the nth root of n to the n divided by n factorial, right? We just rewritten the numerator so that we can include everything in the root, but then we can apply Stolz theorem, because this is going to, the limit of the nth root of this is just the same as the limit. If we call this c sub n, then this is the same, well, let me write it like this. This is the same, applying the corollary to Stolz theorem. This is the same as the limit of c sub n divided by c sub n minus 1. Okay, and c sub n is this, so then we have the limit of n to the n divided by n factorial, and then divided by n minus 1 to the n minus 1 divided by n factorial. Okay, now let me see, this is the limit when n goes to infinity, and then we have n minus 1 factorial, and then divided by n is just 1 over n, so then we have n to the n divided by n minus 1 to the n minus 1. But then n to the n divided by n is n to the n minus 1, right? And then we have this n over n minus 1 to the n minus 1. And then we can rewrite the numerator here as n minus 1 plus 1. So then we have the limit when n goes to infinity of n minus 1 over n minus 1 is 1, and then plus 1 over n minus 1. All of this to n minus 1. Okay, and if you reread your notes, you will see that this is e. Okay, so the same limit that we reached before, and so both ways to solve this are correct. Okay. Now let's see. Three. No, 3, no, we just did 3. 4. The limit when n goes to infinity of let me rewrite this. This is the nth root of 1 over n cube. Okay, and again, just like before, we can rewrite. Well, there's a kind of a quick way if you use what we know in the notes. This is just the limit when n goes to infinity of the nth root of n to the minus 3. But then we know that this limit is 1, this is 1 to the minus 3, or 1. Okay, so you could say this. But another way to do it is, again, apply Stolz theorem here, or the corollary to Stolz theorem. And so this is the limit when n goes to infinity of 1 over n cubed divided by 1 over n minus 1 cubed. So but the n minus 1 goes here, so it's n minus 1 cubed. And it's easy to see that this thing is going to go to 0. Sorry, to 1, right? This fraction. This is n minus 1 over n cubed. So you could rewrite this. This is 1 over 1, sorry, 1 minus 1 over n. And this is going to 0, so this is 1 cubed, 1. Okay? Let's do 5. 5. The limit when n goes to infinity of 2 to the n divided by n factorial. Okay, you could argue here that, again, before, as we have seen in class, 2 to the n is asymptotically negligible when compared to n factorial. And so you could say the limit of this is 0, because that's the definition of this. Okay, you could argue that because we have seen this in theory. But let's try this. Let's see. Wait a minute. So yeah, so the way to prove this is to realize if we start. Let me write this expression. Okay, so this is 2 times 2 times 2 times blah 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 times 2 times 2. Okay, n times, and then n factorial is n times n minus 1 times n minus 2 times, and then whoop, whoop, and then you have 3, 2, 1. Okay, so this term here is 1, this term here is 1, but it's important to see that there are n terms in the numerator and n terms in the denominator. Okay, so all of these terms up to this point are smaller than 2/3. Okay, you have 2/3, 2/4, 2/5, 2/6, and so on. Okay, so this is smaller than okay, sorry, this is 2, this is not 1. 2 over 1, which is 2. Okay, so this is smaller than 2 times, and then 2/3 over n minus 2. Sorry, 2n minus 2, right? So there are n minus 2 terms here, right? So this is smaller than this. This is greater than 0. And the limit, if we take limits here, so the 0 is smaller than the limit when n goes to infinity of 2 to the n over n factorial, smaller than 2 times the limit when n goes to infinity of 2/3 to the n minus 2. And we know that this goes to 0, so this is 0. Okay, so the limit of 2 to the n over n factorial is bounded from below by 0 and bounded from above by 0. So due to the sandwich theorem, we know that this limit is 0. Okay. Okay. Let's do 6. So let's see. How to, yeah, again, so this is the limit when n goes to infinity of n squared over 2 to the n, and you could say that again n squared is negligible when compared with 2 to the n, so this limit is going to be 0. Okay. Another way to prove this is to use Stolz theorem. Okay, this is going to infinity, this is going to infinity, so this is infinity over infinity. We can use Stolz. Okay, so this is the limit when n goes to infinity of n squared minus n minus 1 squared over 2 to the n minus 2 to the n minus 1. So the limit when n goes to infinity of, and then this is n squared minus n squared plus 2n minus 1 divided by, and then we can take a common factor of 2 to the n minus 1, and then this 2 minus 1. This is 1, this and this cancel each other out, and then you have the limit when n goes to infinity of 2n minus 1 over 2 to the n minus 1. And again, you could say that this is negligible, but then because we're doing it explicitly, again, we can apply Stolz theorem again, because this is going to infinity, this is going to infinity. So the limit when n goes to infinity of 2n minus 1 minus 2n minus 1 minus 1, and then 2n minus 1 minus 2n minus 2. So this is the limit when n goes to infinity, and then so you have this thing here is 2n minus 2 minus 1, okay? And so if we apply the minus chains, is plus and plus, so then we have 2, 2, 1, 1, so then you have 2, and below you have 2 to the n minus 2, 2 minus 1, again this is 1. And this is, if you want, this is the limit when n goes to infinity of 1 over 2 to the n minus 3, but this is going to infinity, so this limit is 0. Okay? Okay, let's do 7. 7. The limit when n goes to infinity of n to the n minus 1 over n minus 1 to the n. So yeah, you could try to apply many different tools here, but it's easy to just operate with this directly, because this is n to the n minus 1, so n over n minus 1 to the n minus 1, and then this is multiplied by 1 over n minus 1, right? Now this thing here is going to be, so this is the limit when n goes to infinity of 1 over n minus 1 times the limit when n goes to infinity of, and then this is n again, n minus 1 plus 1, n minus 1 over n minus 1 is 1, and then you have plus 1 over n minus 1 to the n minus 1, so this is just e, but this limit is 0, so this is 0 times e, 0. Okay? Eight. The limit when n goes to infinity of 1 plus 2 square root of 2 plus 3 cubic root of 3 plus blah 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 plus n times the nth root of n over n squared. Okay, and so this is a classical application of Stolz theorem. Okay, whenever you have a sum like this that goes to infinity, the first thing that comes to mind is to apply Stolz. And so when you do this minus this, when the n minus 1 term, the remaining term is this, and then you have n squared minus n squared plus 2n minus 1, which is n minus 1 squared. Okay, so this is cancel each other out, and so you have the limit when n goes to infinity of nth root of n divided by 2n minus 1. So now we divide above and below by n, so you have nth root of n divided by 2 minus 1 over n, and so this is just the same as the limit when n goes to infinity of this divided by 2 minus the limit when n goes to infinity of this. This is going to 0, this is going to 1, so this is 1 over 2. Okay? That's it.